There are two sections left to study for the linear algebra part of the course. The first part is the study of the rotation matrices, or orthogonal matrices, and the second part is the study of the symmetric matrices. In this part of the lectures, we are going to focus on orthogonal matrices, and orthogonal matrices are matrices that are used to describe a rotation or to describe the change of the basis of the Euclidean vector space that we're using. So let's first explain what the function of a rotation matrix is. So as we know, a matrix, the function of a matrix is a linear map between vector spaces such that it transforms vectors, so a matrix M transforms a vector X to a vector Mx. A rotation matrix does the following. If this is an object, it's made out of different vectors, a rotation matrix will take that object and rotate it in space with a certain angle. So rotation matrix rotates vectors and keeps their norms and angles. So after rotation, the angles between vectors do not change, and so the dot product is maintained. The values of the dot product before and after rotation are the same. Another function of the rotation matrix is, or as we're going to study, when we go through the definitions, we're going to present the rotation matrix as part of the family of orthogonal matrices. So for the second function of a rotation matrix, I'll just introduce it as an example. Let's say I have a vector space described by x and y, two vectors as your basis set. I'm going to call this E1, I'm going to call this E2. And there's a vector here. This vector is equal to u, which is equal to, let's say, 5, negative 7, which I can write as 5x plus minus 7y. And let's say somebody else would like to describe the same vector in this coordinate system. X prime is equal to e prime 1, y prime is equal to e prime 2. Now the same vector, u prime, now has two new components. They are not 5 and negative 7 anymore. So let's say these are the two new components, which is equal to this component multiplied by x prime plus this component, whatever that number is, multiplied by y prime. And now if I know the relationship, I want to know, what I'm looking for is the relationship between those components and the original components. What is the relationship between the components u and u prime. It turns out that the relationship is described using a rotation matrix. The relationship is described using a rotation matrix, and as we will show in a bit, that u prime will be equal to a rotation matrix multiplied by u. And it's easy to see that if I know x prime is equal to how many x's plus how many y's, if I know y prime is equal to how many x's plus how many y's, where this is a number, this is a number, this is a number, this is a number, then I can simply say that u prime is equal to this component multiplied by x prime plus this component multiplied by y prime. Instead of x prime, I'm going to put how many x's plus however many y's plus how many x's plus however many y's and if we know that this is equal to 5x plus negative 7y, which is equal to 5 negative 7, you can see that we can relate the old components to the new components using a matrix as follows. The new components are this guy and this guy. Whatever is multiplied by x here will be equal to the whatever is multiplied by x here. So you will find this value, this value, and this value. Well, I'm missing a question mark here. So this matrix of transformation is used to relate the two components, and we're going to see later that this matrix is a rotation matrix and is equal to Q2. We're going to study this at the end of this part of the lectures, but you can see that those question marks or this matrix comes from the relationship between the original basis set and the new basis set. If I know this relationship, if I know the relationship between the new coordinate system and the old coordinate system, I can find the relationship between the old components and the new components using the numbers that relate the new coordinate system with the old coordinate system. So let's step back a little bit now and try to understand or try to define what is an orthogonal matrix. So an orthogonal matrix is defined as follows. if Q is a matrix that's a 3 by 3, now this definition can be extended to an n by n or a 2 by 2, but I'm just going to define it for a 3 by 3 matrix. And we're going to look at the 3 vectors that form the matrix. These are vectors, which, just for illustration purposes, I'm going to draw it like this: A, vector B, vector C. Then Q is called an orthogonal matrix if A, B, C are orthonormal. So from this definition we get some results. What can we say about an orthogonal matrix once we know this definition? What we find is, if this is Q, made out of A, B, and C, and if I take Q transpose, where I take every column or every row, make it into a column, and then if I take Q and I multiply it by Q transpose, let's see what happens. That means every row, I'm going to take the dot product between the row and the column. So what does this give me? This row, A dot A, A dot B, A dot C, B dot A, B dot B, B dot C, C dot A, C dot B, C dot C. Okay, well, when we defined Q, we said that the vectors A, B, and C are orthonormal. What does it mean, orthonormal? It means A dot A is 1. The vectors are perpendicular to each other, so A dot B is 0, A dot C is 0, and so on. So you end up with this matrix. So by defining Q that way, I realized that the transpose of Q is actually its inverse. So Q transpose is actually the inverse of Q. What else? Well, let's see, what is the determinant of Q? The determinant of Q is equal to A dot B cross C, the triple product of the 3 vectors that form Q. And if we check or visit the cross product section, since A, B, and C are orthonormal, you get that A dot B cross C is equal to either positive or negative 1. Positive or negative 1. Now, if the determinant of Q is positive 1, I call this a rotation. And if the determinant of Q is negative 1, I call this reflection. So a rotation and a reflection are both orthogonal matrices. Their inverse is their transpose, and their determinant is equal to 1. or -1. If it's 1, it's a rotation. If it's -1, it's a reflection. So let's look at a few examples. Now, of course, the above applies to any dimensions. Q belong to M. An n by n matrix such that the n vectors are orthonormal. It's going to be the same. If the determinant is 1, it's going to be a rotation. If the determinant is -1, it's going to be a reflection. So let's look at examples in M3. First example is this matrix, the identity matrix, the I matrix. Now what does I do? Well, I takes any vector here, x, you apply I to it, then what do you get? You get Ix, which is the same x. Rotation with an angle that's equal to 0 degrees. I'm rotating the vectors with 0 degrees. Now it's clear the determinant of I is equal to 1, and I multiplied by I transpose is equal to I, which means I -1 is equal to I transpose. It happens to also be equal to I in this particular case. Let's look at another example. Let's say in M3 as well. Let's look at Q cosine 30 degrees, sine 30 degrees, 0, negative sine 30 degrees, cosine 30 degrees, 0, and 0, 0, 1. If I call this vector A, if I call this vector B, if I call this vector C, A dot A is equal to cosine square 30 plus sine square 30 is equal to 1. A dot B is equal to negative cosine multiplied by sine plus sine multiplied by cosine is equal to 0. A dot C is equal to 0. And B dot B is equal to C dot C is equal to 1. Therefore, Q is an orthogonal matrix. And notice, I haven't said it's a rotation or a reflection yet, because that will depend on the determinant. Now, the determinant of Q will be equal to cosine square 30 plus sine square 30, and verify this calculation, of course. You can basically say A dot B cross C, or which is equal to C dot A cross B, or however you want to calculate the determinant. This will be equal to 1, which means Q is a rotation matrix. Now let's give some examples of reflection matrices. And let's look at it in R2. let's look at this matrix. If I call this vector A, if I call this vector B, A dot A is 1, B dot B is 1, A dot B is 0. Therefore I2 is an orthogonal matrix. But the determinant of I2 is equal to -1. I2 is a reflection matrix. So what does it mean by its reflection? Let's see what it does to vectors. I'm going to just draw it on the same vector space, and let's say I have this object that's made out of 3 vectors, vector 1, vector 2, and vector 3. Let's see what I2 does to one of the vectors here. I'm going to assume a general vector. What will happen when I multiply I2 by x? -1, 0, 0, 1, multiplied by x1, x2. You will see when I multiply this row by the column, I get -x1 and x2. Every x, this matrix takes the first component and makes it negative and keeps the positive component. It keeps the second component positive. So every vector, it takes the first component and makes it negative. So we'll take the first vector and we'll put it on the other side. Second vector, and we'll put it on the other side. And the third vector also, we'll put it on the other side. So what do you get? You get a reflected image of the original object. Now, how to construct the next example is how can I construct 2D matrices of rotation. Now this is I have to write a note here. It's very important because that's always a source of mistakes in the exams. Is so here example, constructing rotation matrices or 2D in R2. Note, I'm going to write it in red. Thick note, there is a big difference between rotating or matrices that rotate vectors and matrices that are used for change of basis. Consult next section for the latter. Here we're doing an example in the rotation. So this is how you construct a rotation matrix. If I have E1 and E2, and if I have a vector U, and if I would like to rotate U by an angle theta in the anti-clockwise direction, so this is vector V, which is equal to QU after rotation by an angle theta. Maybe you should use different colors for different vectors. This is vector V after rotation theta. So rotating a vector this way is almost like I'm going to use a trick, which is instead of moving the vector U, I'm actually going to move my basis the other way. I'm going to call this E-1, E-2, or sorry, E-2, E-1. So I'm just, instead of rotating the vector itself, I'm rotating or pretending to be rotating my basis vectors in the opposite direction. Now E-1 is equal to cosine theta E1 plus sine theta E2. E-2 is equal to this is negative sine theta. E-2 is equal to sine theta E1 plus cosine theta E2, and Q is going to be made by E-1 and E-2, which is equal to cosine theta negative sine theta cosine theta. So this is the procedure. This is how I rotate matrices, vectors with an angle theta. And remember, this will be different from this when you actually change the basis, simply because the rotation angle will be the opposite. When you study the change of basis, you're going to get a different matrix. So when you study the rotation matrix, when you study the change of basis, you're going to get a different matrix. For this, for changing for rotation matrices, what you do is, if this is the direction of the rotation that you're looking for, you rotate your basis the opposite direction. After you rotate your basis in the opposite direction, you get the relationship between the new basis and the old basis. From this relationship, you form your matrix Q, and now any vector here, v, is equal to the original vector u multiplied by q. And in another section, in another lecture, I will be explaining how to do all this in Mathematica. Now, in the next section, we are going to talk about now the change of bases. So rather than rotating a vector, I'm trying to find what is the new components of a vector after I rotate it with a particular, after I change the basis vectors. So if I'm living in a two-dimensional Euclidean vector space R2, if I'm utilizing these two basis vectors, E1 and E2, and then if for whatever reason I would like to utilize a different basis vector, E-1 and E-2, and for every vector here, there's another vector here. I'm going to call this vector u. There's another vector here. It's the same vector, but expressed in different components, u prime. And let's say I have a matrix here in the original basis vectors that takes u and gives me v. Then, of course, all these have certain components. Now I have another vector here, v prime, which is equal to the matrix expressed in the new coordinate system multiplied by u prime, which is expressed in the new coordinate system. And of course, v prime has to be v, but in the new coordinate system. So the relationship between these two is done, between the components in both, is done using the translation between, or let's say, I'm going to write it translation between those two languages one expressed in the language of E1 and E2, the other one is expressed in the language of E-1 and E-2. The translation is done using a rotation matrix. In fact, an orthogonal matrix, but usually we keep the determinant equal to 1, so it becomes a rotation matrix. So how can we make that Q? Q is made as follows. I'm going to take E-1 and put it here, and E-2 and put it here, and I'm going to find the relationship between E-1, the first component of E-1, the second component of E-1, the first component of E-2, the second component of E-2. This will be my Q. U prime, which is the components of U in the new coordinate system, which is U prime 1, U prime 2, will be equal to Q multiplied by u1, u2. Now what about v prime or m prime? Well, I know that v prime is equal to m prime u prime, which is equal to m prime qu, because I know that u prime is equal to qu. But at the same time, I want v prime to be equal to qv, because v prime is v expressed in the new coordinate system. At the same time, I know that v is actually the image of u under M. So I have two linear maps. One linear map, M prime Q multiplied by U, and another linear map, QM multiplied by U. Both are equal linear maps. So M prime Q is equal to QM. If I multiply by Q transpose, post multiply by Q transpose, now I know that Q transpose is 1, is I, and these two relationships are the most important. First one is that, and the second one is this. The new components of U denoted U prime is equal to this matrix Q multiplied by U, and the new components of the matrix is equal to Q multiplied by M multiplied by Q transpose. So let's do it through a numerical example. I have a vector x, so this is in R3. I have a vector u, v, and w, and I have a matrix M with these components. So the first question is, so I have a vector x. I would like to find y, which is equal to mx. Well, this is of course direct. Copy the numbers from above. X is 1, 1, 1. Multiply by the row by the column, or take the dot product between this vector and this vector. You get a component. The dot product between this vector and this vector, you get another component. The dot product between this vector and this vector, you get a third component. And this will be equal to .85. I'm not sure if this number is, I think it's 0.85, 0.5, negative 0.25. So this is y. When I transfer x, or when I multiply the linear operator m by x, I get a new vector y with these components. Now, the second question is, we need to show that u, v, w form an orthonormal basis set. Now, is that true or not? To form an orthonormal basis set, that means u and v and w have to be orthogonal to each other, and each should have a length or norm equals to 1. So u is equal to 0.6, 0.8, and 0. V is equal to negative 0.8, 0.6, and 0. w is equal to 0, 0, 1. U dot u is equal to 1. V dot v is equal to 1, which is equal to norm v squared, norm u squared, and norm w squared is equal to w dot w is equal to 1. U dot v is equal to v dot w is equal to u dot w. You have to verify each, and they're all equal to 0. Therefore, UVW form an orthonormal basis set. The next thing is we need the translation. We need to express x and y and m instead of the given components. X is 1, 1, 1, and m is this, and y is 0.85, 0.5, and negative 0.25. Instead of these components, we need to express x, y, and m in terms of u, v, w. So how many u's, v's, and w's are x and y and m? So in order to do this, we need a translation matrix, a matrix to do the translation between the two vector spaces. If this is E1, E2, and E3, and if this is E-1, E-2, then U basis set E-3, where this is U, this is V, and this is W. The translation matrix Q is made by taking the components of U, the components of V, the components of W, which is basically U dot E1. Well, let's just keep our consistent terminology. E-1 dot E1, E-1 dot E2, E-1 dot E3, E-2 dot E2, E-2 dot E3, E-3 dot E1, E-3 dot E2, E-3 dot E3, and this is equal to 0.6. This is these are the components of U, 0.6, 0.8, and 0, negative 0.8, 0.6, and 0, 0, 0, 1. So this is my translation matrix Q. The new components of x prime are equal to qx. So multiply q by 1, 1, 1, and you get 1.4, negative 0.2, and 1. Y prime, multiply q by u, and you're going to get 3 components. What about the new components of m prime? Well, the new components of m prime are obtained by multiplying q by m by q transpose. So you've got a matrix multiplied by another matrix multiplied by another matrix, and you get a new set of components: 0.25, negative 0.5, 0.46, negative 0.5, negative 0.5, 0.22, negative 0.55, negative 0.1, and 0.5. Now I'm going to do an extra step here just to verify that indeed my work is correct. I've calculated y prime using QU. Now remember what y was. This is x. Y was equal to a matrix multiplied by x. That's in the old coordinate system. If this is x prime in the new coordinate system, y prime is equal to m prime multiplied by x prime, which is also which should also be equal to q multiplied by y. So you need to verify that whether you use q y or m prime x prime, you should get the same number. So if I multiply m prime multiplied by x prime, I should get q y, and indeed this is the case. So the last section in this part is the study of vector and matrix invariance. So what does it mean, invariance? Let's say I have somebody who's studying the speed of particles, for example. And let's say I'm using linear algebra, and I have a vector e1 and e2, and I have the vector of velocity v that's equal to, let's say, 2 in the first direction, 3 in the second direction. Now if I use, if the same person or somebody else is studying the velocity of the same particle but in a new coordinate system, they will get two new components, v-1 and v-2. Now these are not equal to the original components, so the numbers are going to be different, but there has to be, now we talked about that translation q translates between the language of e-1, e-2 and the language of e1 and e2, but there are quantities that if you calculate them either in this language or in this language, they don't change, and these quantities are called invariants. And the first thing that does not change is the length or the norm of the vector. So the first quantity that is not affected by the change of coordinate system is the length or norm of the vector. In the original coordinate system, the size of the vector is equal to u dot u. In the new coordinate system, the size of the vector is equal to qu dot qu, which, if you visit section of matrix transpose, will be equal to u dot q transpose qu. Now q transpose q is the identity matrix because q is an orthogonal matrix, which is equal to u dot u, which means it does not change between the coordinate system. So the length of vectors does not change. What else? The second quantity the angle between vectors. If I have a vector u dot v, this is the dot product between u and v in the first coordinate system. In the new coordinate system, the dot product is qu dot qv. Again, visit section of matrix transpose. This is equal to u dot q transpose q u. Q transpose q is equal to I u dot v, which means this quantity does not change between different coordinate systems. So if I have vectors, their length stays the same, and the angle between those vectors stay the same. Now what about matrices? Now matrices are used, for example, to describe stress. Stress, as we are going to study in the next chapter, is described using a matrix of 6 or 9 numbers. Now those 9 numbers, so let's say M is a matrix with 9 numbers. Once I change the coordinate system, I'm going to get 9 new numbers. Totally new. There's nothing in those numbers. There might not be a single number that stays the same. But is there a quantity that can describe that it does not change? Yes. There are, when M is a 3 by 3 matrix, there are 3 major quantities called matrix invariants, that do not change between coordinate systems. And the first invariant is called I1 of M, which is called the trace of M, which is equal to M11 plus M22 plus M33. Which is equal to the sum of the diagonal components of M. So basically, if M is equal to those 9 numbers, and M prime, which is equal to Q transpose in the new coordinate system described by Q, is now equal to 9 new numbers, then if you take those 3 values, you sum them up, and you take those 3 values, you sum them up, this quantity is equal to I1 of M. This quantity is called I1 of M prime. Oh, these are equal. So this is the first invariant. The third invariant, so I'm going to just skip the second invariant for now. The third invariant is equal to I3 of M, which is defined as the determinant of M. Now the determinant of M is equal to the determinant. So the determinant of M, now let's look at I3 of M prime, which is equal to the determinant of M prime, which is equal to the determinant of Q, the determinant of M, the determinant of Q transpose. Now we know that this guy is equal to either 1 or negative 1, and it's the same for this. So you're going to be left with the determinant of M, which means that the determinant does not change its value. The second invariant is a complicated formula, but it's function of the first invariant. I2 of M is equal to half. The first invariant of the matrix M after I square it minus the first invariant of the matrix M after I multiply it by itself. Now, since I know that I1 does not change, I1 does not change between coordinate systems, therefore this is equal to also I2 of M prime. And so these quantities, once you calculate them in a coordinate system, in the first coordinate system, and then you change your coordinate system, the new coordinate system, the new value in the new coordinate system is the same. The last thing that does not change is eigenvalues and eigenvectors. Of course, direction, because the value of the vector itself, the components might change, but the directions do not change. If this x is eigenvector of matrix M, then x prime, which is equal to qx, is eigenvector of matrix M prime, which is equal to qm q transpose. Not only this, if mx equal lambda x, you're going to find that M prime x prime is equal to lambda, same eigenvalue, multiplied by x prime. So the values of the eigenvalues do not change, and the eigenvectors do not change either, they just keep their direction. So that's it for this part. In the next part, we're going to discuss the symmetric matrices, and the symmetric matrices is the last section in linear algebra, and after that we're going to move on to the mechanics part of this course.